Have you ever wondered how it all began? How, from a singularity, we arrived at a universe bustling with galaxies, stars, and life? It's a question that has tickled the human mind for centuries, a question that takes us back to the very beginning, to the Big Bang. The Big Bang, a theory that suggests our universe sprang into existence from a single point, a singularity, around 13.8 billion years ago. But what happened in those early moments after the Big Bang? What shaped our universe as we know it today? The answer lies in the fundamental forces. These are the forces that govern the universe, from the grand scale of galaxies to the tiny particles that make up matter. They are gravity, electromagnetism, strong nuclear force, and weak nuclear force. Each of these forces played a crucial role in shaping our universe, and understanding them is key to unlocking the secrets of the cosmos. So, buckle up as we journey back in time to the very beginning and unravel the birth of fundamental forces. Imagine a state of nothingness, a singularity, and then an explosion of unimaginable scale, the Big Bang. This event, occurring roughly 14 billion years ago, marks the starting point of our universe. It's the moment when all matter, energy, space, and even time itself began. The Big Bang wasn't an explosion in the traditional sense. Instead, it was an expansion, a rapid stretching of space. From a point of infinite density and temperature, known as a singularity, the universe expanded into the vast, diverse cosmos we see today. Picture this. In the first fractions of a second, the universe expanded faster than the speed of light in a period called cosmic inflation. As space expanded, the universe cooled, dropping from temperatures so hot that no current model of physics can accurately describe them. Just after the Big Bang, the universe was a hot, dense soup of particles, a state known as the quark-gluon plasma. It was a swirling, chaotic mix of elementary particles, all jostling and interacting in a sea of immense energy. As the universe continued to expand and cool, the forces of nature began to separate. First came gravity, followed by the strong nuclear force, which holds atomic nuclei together. Then, as temperatures dropped further, the weak nuclear force and electromagnetism emerged, setting the stage for the formation of atoms and the matter we're familiar with. This period, this first second of our universe's existence, was one of the most important in cosmic history. It's when the fundamental laws of physics were established and the basic structure of the universe was laid out. The universe was still far from the structured cosmos we see today, but the groundwork was in place. In this chaotic, high-energy state, the first seeds of the universe as we know it were sown. In the scorching aftermath of the Big Bang, the fundamental forces began to emerge. Picture this. We are now at a point just a blink after the universe's birth, a time when temperatures were unimaginably high, and the universe was a hot, dense state of pure energy. But as the universe cooled, something extraordinary happened. First to make its appearance was gravity, that ubiquitous force that keeps our feet on the ground and planets in orbit. Gravity is thought to have decoupled from the other forces almost immediately after the Big Bang, though its origin remains a puzzle. The source of gravity is believed to be energy created in the Big Bang itself, making it the oldest force in the universe. Then came the strong nuclear force, the mightiest of all the fundamental forces. This force is responsible for holding the nuclei of atoms together. Without it, every atomic nucleus in the universe would instantly fall apart, and matter as we know it would cease to exist. Almost simultaneously, the weak nuclear force emerged. Despite its name, the weak force plays a crucial role in the universe. It's responsible for radioactive decay and nuclear fusion in stars, including our own sun. It's this force that powers the sun's fiery furnace, giving us light and warmth. Finally, electromagnetism was born. This is the force that lights up our world, from the smallest atom to the largest galaxy. It's the force behind light, electricity, and magnetism. It's what makes magnets stick to your refrigerator and allows your computer to compute. These forces, once unified, now distinct, laid the groundwork for the universe's structure. They are the invisible hands that shape the universe from the smallest particles to the largest galaxies. And they continue to shape our universe, guiding its evolution and determining its fate. With the forces in play, the stage was set for the formation of matter. So how did we go from a dense, hot singularity to a universe filled with an array of particles and elements? Let's delve into it. In the immediate aftermath of the Big Bang, the universe was a hot, dense soup of particles, also known as the quark-gluon plasma. These were the most fundamental particles, the building blocks of protons and neutrons, constantly interacting and transforming due to the strong nuclear force. As the universe expanded and cooled, these quarks began to bind together, forming more complex particles. Protons and neutrons were born from these unions. This phase, often referred to as hadronization, marked the birth of matter as we know it. But the process didn't stop there. As the universe continued to cool, another milestone was reached: the formation of the first atoms. This was primarily hydrogen, the simplest and most abundant element in the universe. The protons and neutrons came together to form the nucleus of the atom, while electrons, governed by the electromagnetic force, began to orbit these nuclei. This process, known as recombination, took place about 378,000 years after the Big Bang. It marked the end of the so-called dark age of the universe, as light could now freely travel through space without constantly bumping into charged particles. And so, from a hot, dense point, we now had a universe filled with atomic particles, the building blocks of matter. It's a wondrous thought, isn't it? That every atom in our bodies, the air we breathe, the stars we gaze at in the night sky, all originated from that momentous event nearly 14 billion years ago. The story doesn't end there, though. Stay tuned as we explore how these atoms came together to form the universe we see today. Fast forward billions of years, and here we are in a universe teeming with galaxies, stars, and life. The early moments after the Big Bang were the birthplace of all matter and the fundamental forces that govern it. As the universe expanded and cooled, these forces shaped and molded the cosmos into the complex structure we observe today. From the gravitational pull that binds galaxies together to the strong nuclear force that holds the atoms in your body intact. These forces have been the architects of our universe. They've governed the formation of stars and galaxies, acting as cosmic sculptors, carving out the vast cosmic landscapes we see when we gaze up at the night sky. But the story doesn't end there. The universe continues to evolve, guided by these fundamental forces. Gravitational wave astronomy is revealing new insights about black holes, those enigmatic entities born from the death of massive stars. Meanwhile, experiments at the Large Hadron Collider are furthering our understanding of the subatomic world, potentially providing clues about the elusive dark matter. These modern quests of discovery continue to unravel the grand cosmic tapestry, piecing together the story of our universe from the first microseconds after the Big Bang to the present day. All that we see around us, every star, every planet, every life form, owes its existence to the events that unfolded in the early universe. So what does this all mean? How do the Big Bang and the emergence of fundamental forces matter to us today? In the grand scheme of things, these cosmic happenings from billions of years ago have shaped the universe that we live in today. From the Big Bang's initial flash of energy to the formation of fundamental forces and the subsequent birth of matter, these events have set the stage for the existence of galaxies, stars, and even life as we know it. Understanding these early moments is not just about satisfying our curiosity or filling up textbooks. It's about tracing back our cosmic roots, comprehending our place in the universe, and possibly even predicting its future. The research in this field, be it gravitational wave astronomy or collider experiments, offers us a glimpse into these primal times. Moreover, this knowledge is fundamental to the study of physics itself. It brings us face to face with questions about the nature of time, space, matter, and energy. It challenges our understanding of laws that we consider set in stone and allows us to explore the possibility of their evolution. As we continue to explore and understand our cosmic origins, we get closer to answering the ultimate question: why is there something rather than nothing? If you enjoyed this journey through time and space, don't forget to like, comment, and share this video. Your support helps us bring more such fascinating stories from the cosmos. Until next time, keep looking up.